Welcome back, Physical Science 20. This is the second section in the HT1 booklet. It deals with heat, section 6.2. Okay, so as we mentioned earlier, when objects absorb thermal energy, their temperature goes up. When they release thermal energy, the temperature falls. Okay, so if we take a look down here, let's look at a couple of examples dealing with this idea of thermal energy. If we have two identical nails made of the same substances, and if they have the same temperature, they should have the same amount of thermal energy. So if they're made of the same substances and they have the same mass, they should be fine. If you have two identical nails but one is like twice the mass, and even though the temperature is the same kinetic energy of the molecules are moving at the same speed in both nails, they will have different amounts of thermal energy. Okay? Because you think of it, you have more molecules here vibrating. So even though on average the molecules are vibrating the same way, reading a temperature of 22 degrees C, since you have much more of those vibrating molecules, thermal energy will be higher for the more massive nail. Okay, so that's what I've highlighted here, up here and down here. So of course the more mass nail is more vibrating atoms, etc. So if you have twice the mass, twice as many vibrating molecules, so way more kinetic energy. Therefore, and that leads to more thermal energy. But if you have the same mass and temperature, it'll be the same. So if we take a look at the bottom here, if we look at different substances, okay, so if we're not dealing with, let's say, iron nails, what if we're dealing with iron and aluminum? If you take a look at that, part of the absorbed thermal energy increases the potential energy, some increases the kinetic energy. The proportion of the absorbed energy that goes towards increasing the potential energy of the particles is different for different substances, and what you can add there, therefore different amounts of energy go towards increasing the kinetic energy of the substance as well. So different types of atoms do not absorb energy in the same way. Okay, so that's an important thing to note. The thermal energies will be different. Even though the kinetic energies may be the same, potential energies will be different. Okay, so if we look at this now, distinguish now, kind of up to this point we've been talking about heat and thermal energy kind of interchangeably. Let's look at this more closely though. Heat is a term used to describe the transfer of energy from a warmer object to a colder one. So, and that energy we're talking about is thermal energy, kinetic and potential energy together. So we should use heat. It's the heat that is responsible for how an object is warm or cold, not heat itself. So heat should be used as a verb. The transfer, the movement of thermal energy from one object to another, from warmer to colder. So use heat as the act of transferring and not the energy itself, because that energy is technically thermal energy. Okay? If we look at transferring thermal energy, there are different ways. We'll look at three. Conduction, thermal conduction is the first one, in which the objects have to actually touch each other. So we could have a warmer object, and if it's in contact with a cooler object, the warmer object causes the slower moving particles to speed up because it's transferring thermal energy over. And of course, as that warmer object transfers energy over, the warmer object will then cool down, colder object warms up, and then eventually they reach the same temperature. Unless, of course, you have a source that's continuously transferring thermal energy over. Then, of course, it gets hotter, 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 hotter. If we have something that's already warm, such as a cup of coffee here, the thermal energy will be constantly transferred over to the spoon, and then the coffee will then lose energy, spoon gains, and until eventually they both reach the same temperature. Okay, so conduction has to touch. Convection. Convection occurs when a colder, denser fluid falls and pushes up warmer, less dense fluid. And if you were in class when I talked about this, I did this demo here. With this one example, the blue water here is cooler than the yellow, warmer water. And of course, what happens when I took this card out, the blue water went down to here, and it's more difficult to see, but the yellow water went up until it all mixed, and became a consistent color, which makes sense because warmer water is less dense than colder water. And I also did this experiment in reverse, which I had the cold water on the bottom, warm water on top, and when I pulled the card out, the top stayed. I used actually red and blue as opposed to yellow and blue, but it doesn't matter. The top stayed yellow, the bottom stayed blue. Of course, it would take hours for the temperature to decrease with the warmer water and mix, but for the most part, it stayed consistent like that. There was no mixing of the colors. So what's happening there? We have convection. Warmer water is the particles are moving quicker, so they tend to be more spread out. That makes them less dense. Whereas colder water tends to have slower moving particles, and of course they're closer together, making it more dense. So of course, if we have this constantly happening, water being warmed up, as it warms up it becomes less dense, so it floats up. Colder water, particles move closer together, become more dense, so they fall. So this continuous movement, for example, a pot of water boiling on the stove, you can see it in action. It's called a convection current. Colder water moves downward, warmer water moves up. Thermal energy spreads throughout the liquid. And of course, you can have this in gases too. Near the pavement, the sun would heat up the pavement there, making it hot, and air near the ground would get warm. It would then move up. As it moves up, it gets cooler, comes closer together, gets more dense, and falls. And of course, you can have a convection current there. Convection current, sorry, there. And of course, convection ovens, similarly to movement of air around making a current. Warmer, less dense air moving up, cooler, more dense air moving downwards. And lastly, radiation is thermal energy transferred via electromagnetic waves from sources such as lamps, flames, and the sun. Okay? So let's see, I think that's close to being it. We just have a couple of more things here. Thermal conductors and thermal insulators. If you ever touched a sink in your house, often like your kitchen sink, it's stainless steel and it may feel cold to the touch, and it is a good conductor because what it does is it easily takes the thermal energy from your hand and absorbs it, and of course we feel that sensation as cool. So thermal conductors allow thermal energy to easily pass through them. So of course pots and pans are made of metal because they easily get heated up. They easily take in that thermal energy transferred from the stove element. Whereas thermal insulators do not conduct thermal energy well, do not allow energy to pass through easily. So of course we're talking about wood, plastics, and of course on your pots and pans the handles are made of plastic or wood so that you can grab them without having to get burned as you're boiling water on the stove. Air is also a good thermal insulator as well. If you look at animals down here, this picture of a rabbit, you may be wondering why that's there. In between fur or feathers, air gets trapped, and that acts as a good thermal insulator. So body heat will stay inside the body and not get moved out to the colder environment because we have that layer of fur and air trapped there. It helps make a nice little barrier in between. And of course, in your houses, fiberglass insulation kind of looks furry, feels furry. It has air trapped in there as well. And of course, we could talk about plastic foam insulation as well. It has a lot of air trapped in there, so it helps insulate your house, preventing a lot of thermal energy moving back and forth. All right. So we have wood, plastic, air. Best thermal insulator, though, is a vacuum, which is a space that has all of the air completely removed from it. So if you have a really good expensive thermos, chances are this is what a cross-section would look like if you were to split it in half and take a look at it. Your liquid or solid goes in here. Immediately around it is a vacuum layer, so it has all the air sucked out of there. It prevents a lot of thermal energy from moving back and forth. So if you have a cold object, it prevents thermal energy from moving in, or if you have a hot liquid, it prevents thermal energy from leaving. Also, the exterior of this region would be silvered, so if radiation were to enter, etc., it would be rebounded off that silvered surface. So that's why thermoses are quite expensive to buy, because you can see that makeup likely isn't cheap to make. So having a vacuum between an inner flask and outer flask helps insulate it and prevent thermal energy from moving. Okay. The last part here talks about thermal energy transformation efficiency, talking about furnaces. High efficiency furnace would be one that transfers most of the input energy into thermal energy into your house. Could be 100% efficient. We could have gas furnaces though that are 96% efficient, or if you have older furnaces, only 60% efficient. So all the input energy is only the majority of it is transferred into thermal energy, but of course there's some energy lost. And of course that energy could be lost due to heating up the inside of the furnace itself, or being transferred into another form of energy. All right, so total amount of kinetic energy and potential energy makes up thermal energy of the substance, as we mentioned in this part and also the previous section. Heat is the transfer of thermal energy from a warmer object to a cooler to a cooler object. And of course, the ways in which we can transfer energy is thermal conduction, convection, radiation. All right, so the questions I'd like you to do here are all 5 of them. You should have no problem with that. No calculations even, just simply going through back what we discussed here in section 6.2. Okay, we'll see you again.